Hey everyone, welcome back. Ever wonder why Netflix works smoothly on 2 billion devices? Or how Discord can handle millions of people talking at once? It's not magic, it's this elegant system of networks that evolved from the 1990s to today. And you're about to understand it without writing a single line of code. And I'll do it using just one story. Imagine building a city from a single house all the way to a skyscraper with thousands of residents. That's exactly what we're doing today. Except our city is made of code, and the residents are your favorite apps. We'll kick things off with single server foundations, move into virtual machines and security, scale all the way up to the cloud skyscraper, check out portable container workshops, and finally, navigate our way through the Kubernetes city. So, Section 1, Single Server Foundations. When our imaginary web app first launches, it usually just sits on one lonely physical computer. Now, just like a house literally needs a unique street address for the post office to drop off mail, your server needs an IP address. It's just a special number, something like 203.0.113.10, so that other devices out there on the internet know exactly where to route the data. But let's be real for a second. We humans are terrible at remembering random strings of numbers. I mean, we hardly even memorize our best friends' phone numbers anymore, right? We just tap their name on our contacts. Well, the domain name system, or DNS, is literally the internet's phone book. When you type a normal, human readable name into your browser, DNS instantly translates that name right back into our server's exact IP address, behind the scenes. With that, we've successfully delivered our digital mail to the server's single IP address. Awesome. But what if our one physical server is actually running three totally different programs, like say the public website, a private customer database, and a payment processing system? They are all sharing that exact same IP address. So when a packet of data actually arrives, how does the server's operating system know which specific app is supposed to get it? Well, the secret is all in network interfaces and ports. All network traffic enters the server through the main front door, which we call the network interface. You'll often hear it labeled as something like ETH0. Once it's inside the building, that data has to be routed to specific numbered channels called ports. You can kind of think of these ports as individual apartment rooms inside the building. So, the public website might be hanging out, listening in room 80 or 443, while the database is securely locked away, waiting for instructions in room 3306. The operating system just acts like a really efficient building manager. It looks at the port number stamped on the incoming data and hands it directly to the right room. Boom, problem solved. Alright, let's bump it up to section 2, virtual machines and security. Okay, so our app is growing fast, but relying on just one physical house is honestly a massive risk. I mean, if a hardware part fails, our whole business instantly goes dark. Plus, having our public website and our super sensitive payment data living right next to each other on the exact same physical machine, yeah, that's a security nightmare waiting to happen. To fix this, we bring in virtualization. We basically chop our single powerful server up into multiple virtual machines or VMs. Each VM acts like its own completely independent computer with its own internal private IP address. And then we organize these VMs into subnets. Now, subnets are just a way of doing network segmentation. Think of them like totally separate floors or secure wings inside a hospital. By putting our public-facing web servers in one subnet and our sensitive databases in a completely hidden different subnet, we keep everything cleanly and securely isolated. But hey, just putting things in separate rooms doesn't mean we should leave all the doors wide open, right? We use a layered approach to security here by throwing up firewalls. Network firewalls act like those heavy-duty security guards stationed right at the building's main entrance. They sit right between the public internet and our subnets to block any obviously sketchy traffic. But we don't stop there. We also add host firewalls to protect the individual virtual machines themselves. These are like personal guards at every single room's door, checking every piece of traffic against incredibly strict rules like literally making sure only the web server is allowed to even knock on the database's specific port. So here is the catch though. We've just beautifully secured our internal subnets with private IP addresses, which is fantastic for keeping hackers out, because those private IPs literally cannot be reached directly from the public internet. But wait a minute. How do those 50 highly secured backend servers reach out to the internet when they inevitably need to download a critical software update or verify a credit card with a third party? This is precisely where NAT, or Network Address Translation, completely saves the day. NAT acts exactly like a corporate receptionist. Our internal database sends its update request to the NAT device. The NAT device then temporarily swaps out the server's private address for its own public internet address and sends that request out to the web. When the file comes back, the receptionist remembers exactly who asked for it and securely routes the data right back to the correct internal worker. So the backend server gets its update but stays completely invisible to the outside world the entire time. It's pretty genius. And as the years roll by, our architecture inevitably has to evolve. As we try to manage all these virtual machines and physical hardware, it turns into an absolute nightmare. Trying to predict capacity, buying physical servers, wiring up data centers, it takes weeks. And that bottleneck forces us to completely rethink our physical infrastructure and ascend to the next big layer of our networking evolution. Which brings us to section 3, the cloud skyscraper. To keep up with our crazy rapid scaling, we decide to pack up and move our application into the cloud. Instead of buying land, building a literal structure, and running network cables ourselves, we just spin up a virtual private cloud, or VPC, inside platforms like AWS or Google Cloud. A VPC is essentially like renting an isolated, managed floor inside a massive, highly secure global skyscraper. But, and this is the absolutely crucial takeaway here, the fundamental networking concepts do not change one bit. We are still creating subnets, we are still using route tables to direct traffic, and we are still using managed NAT gateways and firewalls, though now they might be called security groups. The tools are virtualized, sure, but the exact same networking logic applies. Moving right along to section 4, portable container workshops. Okay, so as our engineering team blows up in size, the application turns into this massive, clunky monolith, which leads to that classic dreaded excuse. Well, it works on my laptop, but not in production. To solve this, we break the app down into smaller pieces called microservices, and we pack them into containers like Docker. Now, from a networking perspective, this is a huge shift. A monolithic VM shares one network interface, but a container, it's an entirely isolated network sandbox. It literally has its own isolated virtual loopback interface and its own private IP address, completely walled off from the host server it lives on. It acts like a fully portable, self-sufficient food truck or a toolbox that runs identically no matter what environment you drop it into. But remember, because these containers are happily living in their own completely isolated private virtual networks inside the host machine, external traffic hitting the main server won't just magically find them. If our payment container is listening internally on port 9090, we have to explicitly configure something called port mapping. We basically tell the host server, hey, if any traffic shows up at your main entrance on port 80, I need you to immediately forward it to this specific container's internal port, 9090. It's the vital bridge that connects the outside world to the isolated application running inside that container. Hope you love this breakdown, because honestly, Kubernetes terminology can sound incredibly intimidating at first, but it maps so perfectly to our city analogies. In Kubernetes, the smallest unit isn't actually a container, it's called a pod, which acts just like an apartment sharing a single IP address. Then you have a service, which acts as a permanent department hotline. Ingress serves as the smart mean receptionist routing outside visitors to the right internal department. And network policies, those are just digital security badges ensuring only authorized personnel can enter specific rooms. When you look at it this way, it's really just a highly automated digital city. Let's zoom in on that Kubernetes service for a second because it solves our absolute biggest headache. Remember how pods are super temporary and their IP addresses are constantly changing when they crash or update? Well, if our website is trying to talk to our database and the database pod suddenly gets a new IP address, the connection completely breaks. A Kubernetes service sits right in front of those pods and provides a permanent stable IP address and DNS name that never changes. It acts as a reliable hotline. The website calls the stable service hotline, and the service seamlessly routes that call to whichever database pod happens to be alive and healthy in the background. It's totally seamless. So as we zoom all the way back out, just look at the incredible journey we've taken with this application. Yet whether you're plugging a physical Ethernet cable into a super loud server rack back in 1999, or you're deploying a lightweight microservice to a globally distributed Kubernetes cluster today, these 5 foundational rules dictate exactly how your data flows. The addresses, the names, the doorways, the security guards, and the traffic cops. It really comes down to this. The tools absolutely change. We went from physical routers to VPCs, from hardware firewalls to cloud security groups, but the core concepts, they never change. Once you truly internalize this, once you really grasp these underlying building blocks, you can confidently troubleshoot, secure, or design literally any network architecture at any scale. It's a highly empowering thought, isn't it? Now that you've watched this single server evolve and you deeply understand the invisible blueprint of the digital city, what complex system will you build next? If you found this helpful, don't forget to like, subscribe, and drop a comment if you have any questions. Thanks for watching and see you in the next video.